ladies and gentlemen. Welcome to the deep learning analysis version of analyzing heart failure. Christian is back at it again here. We are actually going to take a deep dive of the heart failure analysis that we have done from the last time when we did the machine learning modeling. Now we're going to actually take the heart failure analysis that we've used, and we're trying to actually dig more into it, into a deeper perspective, just to get a further glimpse on how that model operates for sure. How the data set basically analyzes for sure, and get a glimpse of how deep learning itself can actually impact it. Now, before I actually go dig further into the analysis here, I want to try and get into some definitions, mainly on deep learning, right? So basically, what is deep learning, right? It's an extremely important element of data science, mathematics, statistics, machine learning, the whole 9 yards, basically statistics, predictive modeling, the whole 9 yards, right? It is very, very beneficial to any data scientist, mathematician, statistician, you named it, who are very well tasked in collecting, analyzing, and interpolating large amounts of data. More specifically in terms of the thousands of amounts of data, in terms of the thousands to the millions, to the billions, if they have Amazon Web Services, or they have one of those high level, huge memory computer faces computer interface that they would mainly use when they did their job, right? In order to process extremely huge large amounts of data. Actually, my mentor, who actually is a huge big recruiter, who actually runs a recruiting firm up at that security company, is basically heavily tasked with assigning a bunch of data scientists and a bunch of deep learning engineers, AI engineers, to basically handle this big pool set of data that's literally worth millions. Okay, so deep learning is literally no joke. Okay, that's basically what deep learning is about. In its simplest form, deep learning can be thought of as a way to actually automate predictions and predictive analysis. While machine learning algorithms are mainly linear, deep learning algorithms are stacked in a hierarchy of increasing complexity, abstraction, insanity. You basically name it, right? All this complexity that's actually all is sorted out and clustered, the whole 9 yards. Deep learning will basically take care of that, right? So basically, to understand what deep learning is, right? You know what I mean? Basically, to understand what deep learning is, you have to try and figure out who's basically a toddler basically has a first word, let's say orange or apple, and they try to learn what that word is by actually just pointing to objects and not actually trying to define what it is, right? And the parent has to respond saying, hey, yes, that's an orange, or yes, it's an apple, so on and so forth, or no, that's not a, whatever obviously the baby says. And they continue to point to objects without knowing. He becomes more and more aware of the features that that object possesses, right? That toddler is basically clarifying a complex abstraction by building a hierarchy in which each level of abstraction is created with the knowledge and the education that was actually gained from the preceding layer of the hierarchy, right? An input, and then you got an output, like an input phase, and then you have an output phase, right? So, how deep learning works, right? You basically deal with computer programs that use deep learning to go through much the same process as harder. Basically learn to identify the objects, right? We got each algorithm that actually applies a nonlinear transformation to its input and uses what it learns to create a statistical model known as a output, which is what we define as basically a sequential model, right? Basically mainly put for a plain stack of layers where each layer has exactly one input tensor and one output tensor for a neural network. And within that neural network, what we mean by what a neural network is a series of algorithms that endeavors to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. Thus, we have the toddler, right? So we have the sequential model here, and we already know about what the neural network is. The dense layer is basically the regular, deeply connected neural network layer, right? So hence we have the term, deep learning, right? Where in deep learning is basically mainly unsupervised and complex, right? that actually literally did all the stuff in, right? The computer program can use that deep learning model, right? Within algorithms can be shown within training sets and actually go through millions of images or actually millions of sets, accurately identifying which images literally have those objects that they're actually seeking for within a few minutes or at earliest probably a few seconds, right? So again, big data, cloud computing, the whole 9 yards, and the methods actually deal with deep learning, learning rate decay, transfer learning, basically training from scratch, collecting a large data set, having a dropout, deep learning neural networks, which we already actually discussed, and the whole 9 yards, which we'll actually be digging into today. We'll actually be going through a neural network based on that, right? So what we will be doing when it comes to deep learning in Python here, right? We will be actually focusing more on Keras, right? There's a basically Keras is basically like a software or a package that's mainly used on Python to actually make or predict deep learning models and basically model certain data sets to try and monitor the activity of that data set here and analyze its trends, right? And what Keras is an application programming interface, API for short, that's basically strictly designed for humans, not machines. And what Keras basically, one of the methods that Keras has is a stratified k-fold, which would be a cross-validator, hence the term cross-validating score, right? And then you have the label encoder, which basically converts the labels from words into numbers in Python. Now we have all the data that's basically here. I'll give a quick overview on how things run. We already saw the shape. I'll actually give a quick review later on shortly within the next clip on LinkedIn. And for those as well as folks actually watch up on YouTube as well, to basically discuss how this model basically works, and you basically see it in previous videos on this, right? The usual 13 columns, right? You have the label encoder that's basically set up, and what I will be doing in the next video to come, I will develop a baseline model where I will be manipulating basically the whole data set, whole 9 yards, basically generate the model and evaluate the model with the standard data set that they have here, and go for a baseline where you actually be able to find the mean as well as the standard deviation. And we have two more definitions that I also do want to discuss as well, which are standard scalar as well as Python, right? So the standard scalar, basically what it's basically about, what the standard scalar does, it deals with, right? It removes the mean and scales each feature or variable to unit variance, right? Whereas when you deal with pipeline, right? When it comes to dealing with the pipeline method, right? Pipeline in Python basically has like in which you put together a sequence of steps involved in training a machine learning model, right? Basically automating a machine learning workflow or a deep learning workflow. That's basically what pipeline is, right? You see pipeline and you got the former being standard scalar. And now you deal with the primary standardized data set, we will also actually dig into the second standardized data set to see and try and get a comparison on whether or not it's like much more efficient than the first, and then evaluate the same model with a small topology. And for those of you who don't know what topology is, I know a lot of folks aren't really that mathematically savvy and whatnot. Topology basically states the properties of spaces that are invariant under any continuous deformation, whether it's 2D, 3D, 4D, 5D, 6D, ND, whatever, right? So that's basically what topology is, which could be rubber sheet geometry. And then last but not least, we will deal with the larger model and then deal with the cross validation down at the end. So buckle up, ladies and gentlemen. It is going to be a bumpy. Ladies and gentlemen, let's go dig into the analysis of heart failure via deep learning. As you can see here, right, we already have all the packages already fully loaded onto IPython here, right onto the command screen, and we already have the data set already loaded. Now, let's go ahead and have some fun. The usual shape, we're basically trying to see how big it is. Obviously, around 300, 13 columns, 300 rows. And we understand what the types are. We dig those out, right? All objects as usual, as we saw the last time, right? Now, we go to, and pardon the computer for actually going with a little bit of delay. My apologies for that. Now, we try to see what is causing the problem here. Usual stuff. And they have display with, and they didn't have anything option there because we didn't install it. So what we'll do is we'll just try and delete this guy altogether. Get rid of this guy here. All right, now let's go dig. Get rid of the top row that we had the last time. See what we get. All right, gun. Now we gotta convert all these objects to floats. All right, get this up and running. Boom, boom, boom. All right, now let's get these arrays all set and rolling here. Get the predictors and the respondents. All right. Now what we're going to do here, we are going to use the label encoder, okay, to encode the class values as integers, basically transforming all the words and class values and labels to numbers onto the machine, onto the computer, right? So let's knock this out, see what we get. All set. Now, what we're going to do here is going to create our baseline model here, as we discussed earlier, and get that knocked out and see what we have. All set. Now we evaluate the model with the standardized data set, right? Get that out the way. Let's see what we get here. All right, let's see. Get the mean and the standard deviation up there. Okay. All right, baseline. The mean is at 61.21%, while the results of the standard deviation is at 10.22%. Let's see if we can try to get a better model with better efficiency here. So what we're going to do, we are going to import the standard scalar and pipeline and see if we could try to manipulate the model with our second data set here. All right, so far so good. Now, what we will do, we are going to now evaluate this model with the second standardized data set here. We involve the estimators and see what we get out of this one. Let's get it going. All right. Now we got like a much better baseline model. We have one coming up at the mean coming up at 80.95%, with a standard deviation of 5.34%. Right, so we do have a higher mean with the higher model that's there here. Right, so what we'll do, we'll create a smaller model and see what we could get out of this, basically with the heart failure data set, and see what type of methods that you use to actually play with. Right, let's run it. All right, so far so good. All right, once we did the small model evaluation, take notes. What I have done, I've ran a smaller model by actually basically slicing the columns in half. Right, so that's what I basically did. I created a small topology by actually slicing the columns in half of the heart failure data set, and basically see if I could try to return the model out of this. Now we need to evaluate to see what outcomes we can get. All right, so let's see if we can try to run this model here and see what we can get out of it. All right, so the small topological model, excuse me, we have the mean coming out to 77.61%, and the standard deviation coming out to 4.89%. Right, now let's focus on the larger topological model, right, where we add a bunch of manipulations here, mathematical manipulations, going through neural layers, basically going through one column here, half the column, and the full column, right? So that's basically what the larger model will be. So let us run the final outcome and see what we can get out of this one. All right. So the larger topological model, excuse me, I'm trying to get the topology right. The larger topological model right here, basically with the mean is going to come out to 76.26% with the standard deviation of 7.49%. So comparing all the models that we have together, right, the baseline model, right, this baseline here, with the pipeline model would add it with the baseline model that's used for heart failure, has approximately a 81% mean verification rate when it comes with cross validation. Basically see how legitimate that data set basically is. And in closing, right, I want to try and explain this in a way. As I know this stuff can be a bit depressing when you're dealing with, because again, the numbers that you see and the statistics that you see on those graphs, they're not just numbers, as I stated earlier. They're people, right? They're family members, their aunts, their uncles, their cousins, their sons, their daughters, their fathers, their mothers, siblings, the whole 9 yards, close friends, good friends, you name it, right? And the thing of it is, this is very important for the public to know by predicting the mortality rate, by actually trying to see whether or not that data set is actually verifiable for actual doctors and nurses and public health specialists to literally follow, just to make sure that they would try to use that method to try and figure out ways on how to better improve the lives of patients via health, whether it be medication, whether it be organic medication or medication coming through a pharmacy, those types of things. It basically deals with the verification of that to try and make sure that mortality is limited, try and make sure virtually there's no mortality involved at all. But at least, we could try to minimize the mortality rate by that on basically what can be done in order to help save more lives. You know what I'm saying? You know what I mean? Understand? So, with that, this is the whole end of the whole heart failure analysis. I hope everyone takes a note. Everyone takes note on basically what they have learned so far and actually have some intellect on basically what goes on. And also feel free. You're also welcome to actually share all these statistics to the general public. And for more information, you can always look on my site through GitHub, and you'll be able to see all of the full data sets from there. You're always welcome to actually may have your twist on that and basically try to share that data set and the Excel graph and try to make your own analysis of it as well, and try to analyze your own viewpoint. I actually welcome that so that we'll be able to actually improve our viewpoints and learn from other methods, see what we can do better moving forward. So with that. It's I know it's a very tough time when it comes to health, but I promise you these next couple clips coming up, hopefully they will be fun coming down the pipe. So with that, Christian Paul is signing out. See you next time.